Okay, let's begin with this then. So what have we done in integration? We started with these basic rules that are given in the formula sheet. Some are given on the integration page, and then there are others that are there on the differentiation page. When you reverse them, you get these rules. You should be able to use these rules to integrate functions. Now, in all of them, the condition is that x can be replaced with some other linear expression, and the rule will work. There will be one additional step, and that will be that you would divide by the derivative of this expression as well, along with using the rule that's given in the question, given in the formula sheet. For example, if you have sine of ax plus b, integration of that is going to be minus cos of that, but then you divide by a as well. And similarly, for all the other rules, this is what we started from. Then we talked about the ln rule, which is when numerator is the derivative of the denominator. In that case, the derivative is given by the integral is given by ln of the denominator, right? We did a number of examples in this. You need to remember that tan and cot both are integrated using this rule as well. We talked about the tan inverse rule. This is the condition for using that constant over x squared term plus some constant. That's the condition for using tan inverse rule. And this is the format for that. We did a number of examples in this. And then integration using partial fractions when you have factors in the denominator. Integration, and in that we had two specific other forms as well that are directly given in the formula sheet. These two forms. When you have x squared minus a squared minus x squared in the denominator, you can write down their integrals directly from the formula sheet. That's what we did. And then integration by splitting the numerator. Sometimes you have multiple terms in the numerator. You can split them and convert them to multiple fractions, and then integrate those fractions individually using one of the other rules. Improper fractions, for this you use quotient plus remainder over divisor, right? And then integration by parts. This is the formula for that. Integration of u v dash, that's uv minus integration of vu dash. How do you decide between u and v dash? I late. The one on the left is u, the one on the right is v dash. Sometimes you have to use integration by parts twice as well, because once you integrate once, then you can still get a product, and then you have to integrate it once again. ln x and tan inverse, both of them, they are integrated using integration by parts rule. You need to remember this, right? Again, something that you need to keep in mind. Whenever you have to integrate ln x or tan inverse x, you write them as 1 into ln x, 1 into tan inverse x, and then integrate using integration by parts. Then we did this loop method, in which when you have an integration, in which when you apply integration by parts, it does not become simpler. You try to see if you can get the original thing back again, and then you can use this loop to find the integral. For example, if the original integration was I, you replace this thing with I again, and then make I the subject, right? We did a couple of examples in this. Sometimes it happens after doing one step of integration by parts. Sometimes it happens after you have applied integration by parts twice, that you get the same thing back. This was the other example that we did for this, right? So you need to know all of these rules. Then this extended power rule that we did in one of our classes, and that was, if you have something of this form, when you have an expression and a power on top of that, and you have the derivative of this base multiplying outside as well, then the integration of this is just this power n plus 1 divided by n plus 1, right? And this can be used to simplify some integrals. We did some examples of this. Integration by substitution, right? We did this in the last session. You will be given a substitution in this case. You would have to differentiate that first of all, then replace dx with du as well using that derivative, and then find the integral in that substituted form. And then if you have limits, you have to change the limits as well. Sometimes the smaller number becomes the upper limit, bigger number becomes the lower limit. If you have to switch them, this is the rule that you use for that. You multiply that thing with negative. and then you can switch the limits, right? If you switch limits, the whole function gets multiplied with negative. That's what we did. And then this was one example of that where we have to switch the limits. Then we talked about integrating odd powers of sine, cos, tan. Odd power is there's only one in your syllabus, and that's cube. Sine cube, tan cube, cos cube. How can they be integrated? You can integrate them using substitution, but you would have to remember the substitutions in this one case. For sine cube, you use the substitution u equals cos x. For cos cube, you use the substitution u equals sine x. And for tan cube, you use tan x. We did these integrals. Then we talked about even powers of sine, cos, and tan at the end. Sine squared, cos squared, tan squared. These are in sine and cos, they're even powers, power 2 and power 4. They are integrated using the double angle identity for cos. For square, we have to apply this identity once. For power 4, we have to apply it twice to first convert it to cos 2x and then cos 4x, and then integrate that. This is what we did. And for tan squared, you can just replace that with secant square x minus 1, and then integration of secant square is tan. So that's a lot. If you understand all of this well and you remember all of these rules, then you will see that integration will become easier for you. But this is a prerequisite for this. If you start solving past paper questions, start trying to solve past paper questions randomly without knowing all of these concepts, then that's the reason people find it difficult, that they just jump into questions without actually remembering all of these rules and remembering their conditions. And then they think that they can't do it because it's very difficult. They can't figure out what to do. Once you have all of these rules in your head, then anything that you get, you can somehow fit that into one of these cases that we have done. And that comes with knowing the rules and then doing a lot of practice. Okay, so make sure that you're doing that. Now, let's do some questions today. That's the plan for today. We will just be doing past paper questions. What I'll do is, before that, I'm adding here a page that you can look at in your own time later. That basically summarizes most of those rules. Do I have that here anywhere? Substitution plus P3. Okay, might be here then. Yeah, so this is the summary of most of those rules that we have done. I've added this page to OneNote. So for revision later on, you can have a look at this. Basically, how do you decide which rule to use when it's a simple function without any product or fraction? You use the direct formulas in the formula sheet. The first thing that we did, the first page of our notes. If it's a product, you either have to use substitution or integration by parts. If it's substitution, it will always be given. Otherwise, you use integration by parts or that extended power rule. In some rare cases, you might find that makes things quite simple as well. If you have x something raised to power n, this was that extended power rule that we did. And then you have the derivative of that base multiplying outside. This is given by this power n plus 1 divided by n plus 1 plus c. And that was one rule as well. For products, you can use one of these. If it's substitution, it will always be given. Otherwise, you can either use integration by parts or this extended power rule. For fraction, you have all of these different possibilities. It'll either be substitution, in that case, it will be given, or the ln rule, tan inverse rule, partial fractions, and then after partial fractions, you can do ln or tan inverse rule. And then you can use one of those two forms written in the formula sheet directly for partial fractions. You can split the numerator. You can use you can use quotient plus remainder over divisor in an improper fraction. If none of those things work, you just take the denominator to the numerator, right? And then either integrate that directly or using integration by parts. And then even powers of trigonometric functions, they are integrated using trigonometric identities. In particular, sine and cos are integrated using the double angle identity for cos. I've added this in the notes. You can go through that and make sure that you know all of those rules that you have. Let's jump into some questions now. So I have 2 in the chat until now only, and that tells me that you've not been practicing enough. But okay, let's look at them now. P3 integration. P3 integration. Okay, so this looks like a relatively easy one. Huda, are you sure you're asking about this one? Question number 18. Is it from this worksheet or the other worksheet? Question 18 from this worksheet or other worksheet? Okay, the other one. Let me see if I can open that other worksheet. Okay, let's start with this one. This is May, June 2020, paper 3, variant 2, question number 6. Question number 18 from this worksheet. We're doing this first, and then question number 28 from the other one, from the old worksheet. Yes, Ibrahim, that's what it is. If you remember the rules, you should be able to spot almost all of them without having to think a lot. So you need to remember the rules and also do a lot of practice. Okay, let's start with this one. It says the diagram shows this curve y equals x over 1 plus 3x whole raised to power 4 for x greater than or equal to 0 and its maximum point m. Find the x coordinate of m, giving an answer correct to 3 decimal places. Okay. What about part A? Do you want to ask about part A as well? Because that's differentiation. Can we skip that and just do the integration one? Do you want me to do the... Yeah, okay. So let's skip the first part because that's just finding the maximum point. You find the derivative of this, put that equal to 0. You can do this using quotient rule and then put that equal to 0. So I'll skip that part. Let's look at the next second part. It says using this substitution, u equals square root of 3x squared, find by integration the exact area of the shaded region bounded by the curve, the x-axis, and the line x equals 1. You can see the shaded region on this diagram. This is what we're looking for. Area between a graph and x-axis, what is that given by? What's the formula that we have for that? You've done that in paper 1, not in O-levels. The formula was integration of y with respect to x, right? Limits are from 0 to 1. These are the limits that you have to input. And the function is y equals x over 1 plus 3x raised to power 4. This is what we have to integrate from 0 to 1. Okay, let's input that function here. It becomes x over 1 plus 3x raised to power 4 with respect to x. That's what we have to integrate from 0 to 1. And they've asked you to use the substitution that u equals square root of 3x squared. Let's do that. Remember what we do in substitution? We first of all have to differentiate it, right? Find du over dx and see what that is. Du over dx. What would that be? The number that's multiplying, that remains as it is. You multiply by the power, subtract 1 from the power, that's just x, and that gives you 2 under root 3 times x. Okay. Now, we want to eliminate dx from here, right? How do we do that? We make dx the subject here. So we have du over dx equal to this. If we make dx the subject, that would give us du over 2 square root of 3 times x. This is what we get. And now we put this substitution there. We say u should be equal to square root of 3x squared. So we will do this substitution, and dx should be equal to this thing. Okay. Now we'll talk about the limits in a moment. Let's actually do the substitution first, and then we'll convert the limits as well. Let's not write the limits for now. Square root of 3x squared, that is what we need to replace with u here. Now, what do we have here? We have 3x raised to power 4. If you think about it, if I square this thing, this becomes u squared equal to 3x raised to power 4. So that tells me that I can replace 3x raised to power 4 with u squared. Okay, that's what we can do here. Let's do that. So I can replace in the denominator 3x raised to power 4 with u squared. So in the denominator, I have 1 plus u squared. All right. Now let's replace dx with this thing as well. What does that become? du over 2 square root of 3 times x. These are the two substitutions that you will always do. The one that's given, and then the derivative. Using the derivative, you make dx the subject and replace that there as well. And now you see x and x, they get cancelled, and we have everything converted to only in terms of u. 1 over 1 plus u squared whole multiplied by 2 square root of 3 times dx. We have to integrate this with respect to x. Now to simplify this, I can write this constant outside, right? That's just a constant that's divided by the whole thing. That's being divided by the whole thing. We can write that outside like this, 1 over 2 square root of 3. And inside we're left with 1 over 1 plus u squared. We have to integrate this with respect to u. Does that remind you of something? 1 over 1 plus u squared. 1 over 1 plus u squared. What form is that? That's tan inverse form, right? Where was that? Yeah. This is the form that you have in the formula 1 over x squared plus a squared. That integrates to this, but that's actually a simpler form. That's given in the differentiation page as well. If you remember, when we did differentiation, in differentiation, they used to say the derivative of tan inverse of x is 1 over 1 plus x squared. So if you go back here, this should just be tan inverse of x. But if you want to use the integration rule that's given in the formula sheet, that's how you would use it. The integration rule tells you that you need to have 1 over x squared plus a squared. Integration of that is 1 over a times tan inverse of x over a. But you see, what's the value of a here? A is basically 1, right? So we can write 1 as 1 squared. So a is basically just 1. So if a is 1, we're just left with tan inverse of x here. In this case, the variable is u. So we can say it becomes 1 over 2 square root of 3 times tan inverse of u. That's the integration that we get from this. Okay. Now, what about the limits? What about the limits? Now, let's change the limits as well. If you feel you might forget changing the limits and you might just input 0, 1 here, make it a habit to evaluate the limits alongside this working in the very beginning so that you don't forget later on. What's the lower limit and what's the upper limit? You have to clearly write them so that you don't mix them up. Lower limit was x equal to 0 and the upper limit was x equal to 1. U is equal to square root of 3 times x squared. So square root of 3 times 0 squared, that just gives us 0. So the lower limit is going to be 0. upper limit u equals square root of 3 times 1 squared. U is equal to square root of 3. The upper limit is square root of 3. Okay. And now you can input these limits there in that integral and you get the result. It wasn't that difficult. We want the exact area, so make sure not to use decimals here. What do we get? 1 over 2 square root of 3. Limits are from 0 to square root of 3. And that becomes tan inverse of square root of 3 minus tan inverse of 0. Let's simplify this. 1 over 2 square root of 3, keep that outside. Tan inverse of square root of 3, you can put this on your calculator. I think this is pi over 3, right? Pi over 3, and then tan inverse of 0 is just going to give you 0. And that simplifies to pi over 2 into 3, which is 6 under root 3. You can leave it like this, or you can write it in rationalized form. The way to do that would be just put this on your calculator, and your calculator is going to give you something like this. It will give you square root of 3 pi over 18. Okay, you can just put that on a calculator and it should do it for you. Yeah, pi divided by 6 under root of 3. And that, okay, it's not giving us that form. Okay, let's remove pi from there. That might help. Let's have 1 over this. Yeah, it simplifies it to under root 3 over 18. And then you can put pi with that yourself. Okay. Any problems with this? So once you've done practice, you will find that this is not one of the more difficult questions. It's like average difficulty. Once you've done a lot of practice, of course, that's when you will find this not that difficult. Okay.
Sir,
Yes.
in rationalization, we just multiply by the square root in the numerator and the denominator.
Yes, in this case, yes, we could do that. Just multiply by square root of 3 and divide by square root of 3, yes.
Okay.
But it's not required that you show working for this. Generally, your calculator will do it for you. So you just put this on your calculator and just use the result from there, and that's okay. Okay, that was question number 18. Let's move on to the next one. Next is 28. I need more questions. Okay, sorry. I missed this. We cannot split the fraction. There's pluses in the denominator. Yes, of course, we can't split this. Okay, so please remember this. If you have 2 plus, or let's say 3 plus 5 over 2, that's the same thing as saying 3 over 2 plus 5 over 2. These two are equivalent. However, if you have 3 over 6 plus 9, that's not the same thing as saying it's 3 over 6 plus 3 over 9. These two are different things. We can't split the denominator like that. Or let me use a more obvious example. Let's say we have, 2 over 1 plus 1. If I have this, you can't say it's the same thing as 2 over 1 plus 2 over 1, right? That's clearly wrong. You cannot split the denominators like that. You can only split the numerator. Okay. All right, let's look at the next one. Question 28. That's the other one that you guys are asking about. But that's from the other worksheet. This one. Okay, 28 from the worksheet. Let's try this now. All right, it says The diagram shows the curve y equals x squared into e raised to power minus x. Show that the area of the shaded region bounded by the curve, the x-axis, and the line x equals 3 is equal to this. Again, we need to find the shaded area. How do we do that? It's the area between the curve and x-axis. We know the formula for that. That's integration of y with respect to x, limits from 0 to 3 in this case. Okay, let's try that. So we have to find the area like this. It's going to be integration of y, which is this. It's x squared into e raised to power minus x. Limits are from 0 to 3. Yeah, so that's what we have to evaluate. Okay, now how do we do this integration? It's a project. We would have to use integration by parts for this. Okay, and looking at this, it tells me since it's x squared that's multiplying with this, we would have to do integration by parts twice. Okay, but it's okay if you can't figure that out yet. Just apply integration by parts and see what happens. It's a product, right? So we use integration by parts. How do we decide which one to take as u and which one to take as v dash? Let's use I late. The one on the left side and I late should be u, and the one on the right side should be v dash. One function is x squared, that is algebraic. And the other function is e power minus x, that is exponential. So that the exponential function should be v dash and algebraic should be u. Let's write that down on the side. U is equal to x squared and v dash is equal to e power minus x. Okay. Now, what's the formula? What's the integration by parts formula? Integration of uv dash is uv minus integration of vu dash, right? So when we apply the formula, it's going to look like this: uv minus integration of vu dash. Let's input values in this. For that, we need u dash. U is equal to x squared. What is u dash going to be? Derivative of this is 2x. V dash is e power minus x. We want to integrate this now. E power minus x divided by minus 1, which is the derivative of minus x, right? We have to divide by that. And that simplifies to e power minus or minus e power minus x. So now we've got everything that we need. Let's input these values here. In place of u, input x squared. So you get x squared times v, which is minus e raised to power minus x, minus integral of v, which is minus e power minus x, times u dash, which is 2 times x. We want to integrate this with respect to x now. Okay, now before we do anything else to this, let's simplify first. That will save you from careless errors. Let's do the simplification first of all. Minus x squared into e raised to power minus x. This is minus, it becomes plus outside. 2 is a constant, we can write that outside as well. Again, to simplify things a bit. What are we left with inside now? E raised to power minus x times x. This is what we have inside this integral. This is still a product. So we would have to use integration by parts on this again, right? It's still a product. But now at this point, you will see, is it getting simpler or not? Is it simpler than before? Because if it's not getting simpler, then you might be doing something wrong. We started from x squared e power minus x, and now we have x into e power minus x. So the power of x is reduced. That means we are going in the right direction. In the next step, x can be eliminated. Okay, again, use I late. X is algebraic. E power minus x is exponential. So again, we will take u as x and v dash as e power minus x. Now we have already integrated this above. U dash turns out to be 1, and v will turn out to be the same thing again, which is minus e power minus x. Let's use integration by parts again. So now we have minus x squared into e raised to power minus x plus 2 times u into v. U is x into v, which is minus e power minus x, minus integration of vu dash. V is minus e power minus x times u dash, which is 1. Bracket closed. Let's simplify this. Minus x squared e power minus x plus 2. Keep that outside for now. Inside we have minus x e raised to power minus x, minus into minus, that becomes plus. Inside the integral, what are we left with? E power minus x. What's the integration of e power minus x? E power minus x divided by minus 1. Or we could just change the sign to a negative as well once we figured that out. I'll just leave it like this so you know what we are doing. Okay, integration is done now. Now we have to input the limits from 0 to 3. Again, I would recommend simplify this first and then input limits. Minus x squared e power minus x minus 2x e power minus x. 2 into this, we have a negative sign here, right? So it will be negative 2 e power minus x. Do we have any same terms here? No. Okay, so this is the final integral. Now we can input the limits. Limits are from 0 to 3. Okay, let's input 3 first of all. When we input 3, we get minus 3 squared. Remember, minus is outside the square. So the negative sign here is going to remain. Okay, so it's like this. It's minus and then 3 squared times e power minus x. That would be e raised to power minus 3 minus 2 into 3 into e power minus 3 minus 2 into e raised to power minus 3. That's what we get when we input x equal to 3. Subtract from this the case when we input x equal to 0. This becomes 0. This also becomes 0. But the last term does not become 0. Do not write that as 0 because we don't have x multiplying with this. The last term would be minus 2e raised to power 0. Okay, now let's simplify this further. We get minus 9e raised to power minus 3. What do we want at the end? Okay, e cube in the denominator. All right, so we have minus 9. Let's keep it like this for now because we have more terms like that as well. Minus 9 e power minus 3, minus 6 e power minus 3, minus 2 e power minus 3, minus minus plus 2 into e power 0, which is just 1. Simplify this. This becomes minus 17 e power minus 3 plus 2. And that can be written as 2 minus 17 over e cube. And that's what we wanted to prove there. That's your final area. Is that okay? Any problems with this? No problems? Okay. Do you want me to do the second and third parts as well? Because they're not integration. Part 3? Okay. The second part says find the x coordinate of the maximum point. That's straightforward. Find the derivative, put that equal to 0, solve that equation. We've done a lot of that in differentiation before, so I'll skip the second part, assuming you can do that. Part 3. Let's look at part 3. Find the x coordinate of the point P at which the tangent to the curve passes through the origin. Okay, so we have a point P on the curve. And it's such that if you were to draw a tangent at this point, it would pass through the origin. We have to find the x coordinate of this point P. What's the x coordinate here? That's what we're looking for. Okay. All right. Tangent has to pass through the origin. That means the y-intercept of this tangent should be 0 at this point. Okay. First of all, we will need the gradient of the curve, right? Because when we talk about tangents, we need to find the gradient of that tangent. For that gradient, we need the gradient of the curve at this point. So you would have already differentiated the function in the second part to find the maximum point. Okay, so we're not supposed to do that again in the last part because it's only 2 marks. So you've done that work in the second part already. Okay, so you're telling me the derivative is, okay, let me write that down here. dy over dx, you're saying that that is equal to x e raised to the power minus x into 2 minus x. That's dy over dx. Is that correct? Is that the way I should write it? Okay, yeah. X e power minus x into 2 minus x. That's the derivative that you have found in the second part. Okay. Now, what would be the x coordinate of P such that the tangent passes through the origin? Okay, now one thing that I can think of is I can say this point P has some coordinates like this, that it is x and the y coordinate would then be x squared e power minus x, right? That's the y coordinate. If the x coordinate is x, the y coordinate is supposed to be x squared into e power minus x. Now, using this point P, can we write down the equation of the tangent in terms of x and e, of course? If the point P is x and x squared e power minus x, can we write down the equation of the tangent using that? Let's try that. So point P is such that, or maybe instead of that, we could use the origin and then use this there and then put this. Okay, it works both ways. X, the coordinates of x of P can be x squared e power minus x, right? Every single point on the curve is of this format, that the x coordinate is x and the y coordinate is x squared e power minus x. Okay. Can we write down the equation of a tangent that passes through this point, and has this gradient? We're not assuming anything here. Okay, we can't assume that x is equal to any value, but every point on the curve, its x coordinate is x and the y coordinate would be this, right? So it's not any assumption, it's true for every single point on the curve. We have to find the value of x at which this tangent would pass through the origin. Now, how do we do that? This is the derivative of the curve. You can say this is the gradient of the point P in terms of x. Of course, we don't know the value of x. Using this and this, can we write down the equation of that tangent? What would that be? Y minus y1 equals m into x minus x1. Of course, we're going to write that in terms of x. Okay. The point that we have is this. This is x1 and y1. And this is the gradient, this whole thing, in terms of x. Let's write this down. What do we get? Y minus y1, which is x squared into e power minus x. That equals m, which is xe power minus x times 2 minus x times x minus x. Okay, that does not give us anything interesting. Okay, so it's all getting cancelled out here. So that's not going to help. Okay, let me think of something else then. Okay, so another idea could be, so this is not working. Let me tell you again why that's not working, because on the right side, I'm getting x minus x. That's becoming 0. And I'm left with x squared e power minus x and 0 on the other side. And that gives me the same curve back again. So that's not helpful. So we have to do something else now. This is not working. Okay, let's think of it another way. Let me remove this part. Okay. Now, if the tangent at P has to pass through the origin, another way to think about this could be, that the gradient of the curve at the point P, should be the same as the gradient of the line OP. It should be the same as the gradient of the line OP. Now, what are the coordinates of P that we wrote there? We said that the coordinates of P are this. What's the origin? Origin is just 0, 0. What we can do is we can say, let's find the gradient of OP line. If it passes through the origin, the tangent, we can find the gradient of the tangent using the gradient of the line OP. We have 2 points on the line. One is O and the other is P. Right? How do we do that? y2 minus y1 over x2 minus x1. Let's see what that gives us. X squared e power minus x, that's y2, minus y1 over x2 minus x1, which is x minus 0. And that gives us x squared e power minus x over x, and that's x e power minus x. The gradient of OP should be this. Okay, gradient of the line OP is x e power minus x. We are saying that the gradient of the curve at this point should be the same as the gradient of the line OP. Only then the tangent would pass through the origin. So what we can do now is we can say the derivative that we got earlier, it should be equal to this gradient OP. Gradient of the curve at P should equal the gradient of line OP. What's the gradient of the curve? That's the derivative x e power minus x times 2 minus x. That should equal x e power minus x. All right. Now we can solve this equation and see what we get from that. Since we're looking for this point x, x cannot be 0. So that was x squared. That's x e power minus x. Can anyone spot a careless error anywhere here? Because it looks like... Okay, no, this is fine. So I was thinking that it would be x equal to 2. No, it'll be not x equal to 2. Let's solve this equation. How do we solve this equation? I can cancel out this whole thing like this. Why can I do that? Generally, we don't cancel out x, right? But in this case, I can do that because I know that x value at this point is not supposed to be 0. So it's okay to divide by x in this case, because we know the x that we are looking for is not 0. So I can just divide this on the other side and everything gets cancelled out. So 2 minus x equals x e power minus x divided by x e power minus x. These two get cancelled. What are we left with? 2 minus x equals 1. And that gives us x equals 1. At that point P, the x coordinate is supposed to be 1. Okay, so I was actually in my head when I was verifying this, I was thinking it will become 2 minus x equal to 0, but it's 2 minus x equal to 1, of course, not 0. So that gives us the correct value. So if you get 2, the graph would not make sense. So I was just thinking if this is 3, then how can you have 2 here? Because it doesn't make sense on the graph then. But it turns out on the right side of the equation, instead of 0, we would get 1, of course, when we cancel that out. So we get x equal to 1. That's our final result. Okay. So we just equated gradients, yes. The gradient of the curve at that point and the gradient of the line at that point. The 0 rule, okay, so the question is, what was I saying about 0 earlier? Yes, whether that's okay. What was I saying about dividing by 0 earlier? That is that we generally avoid dividing by x. Let me give an example of that. Let's say you have an equation like this. x squared equal to 2x. Now, if you divide by x, it would become x squared over x equal to 2, and you get x equal to 2. That would not be the correct way of doing this. Why? Because in this case, you are missing out on one possible answer. You should actually do it like this. You should bring 2x to the left side, take x common, and that gives you either x equal to 0 or x equal to 2. So if the value of a variable can be 0, you don't divide by that, because if you divide, then number one, it can become undefined if the value of that variable becomes 0. So we avoid dividing by x for that reason. We can only divide by x if we are sure that the value of x, the value of that variable, cannot be 0. In this case, we knew that x cannot be 0 because on the graph you can see the x coordinate of P is clearly not 0. So that is why I said we could do this division. Otherwise, the proper way of doing this would have been to do something like this: x e power minus x into 2 minus x, and then you would bring this to the left side as well, equals 0. Then you take x e power minus x common, that leaves you with 2 minus x minus 1 inside. And that means either x equal to 0, this factor, or e power minus x equal to 0, or 2 minus x minus 1 equal to 0. So you get x equal to 0 as one solution, and you get x equal to 1 as another solution. This does not give you anything. And then you would say that x equals 0 is not possible because the coordinate of P has to be positive. And then you would ignore this as well, and you get this answer. In this case, since we knew that x cannot be 0, we just divided by x for that reason. Is that all right? Okay. If we did not know that x cannot be 0, then you would actually do it like this, right? Otherwise, you will miss out on this x equal to 0 answer. So generally, you don't divide by x, okay? Because you can miss out on a possible answer using that.
Sir?
Yes.
Does this go for tan trigonometric functions too?
Yes. In that case, when we divide by cos x, sometimes, if you're referring to that, sometimes we divide an equation by cos x, right? To convert it to tan somehow. When we do that, there's a condition for that cos x cannot be 0. So whatever we are dividing by, we are basically saying that value cannot be 0. And that is why in the formula sheet as well, if you see, I've not copied it here probably, but you will see in the actual formula sheet, they would have clearly written tan theta is identical to sine theta over cos theta, but cos theta is not equal to 0. So that's a condition for this to work.
Okay, sir.
So if you're dividing by cos theta, you are using that condition that cos x in that case cannot be 0. So anything that you divide by, you have to be sure that cannot be 0. Otherwise, you get problems. Okay, any other questions? Any other questions? Okay, let's do some of these now. Yeah, the loop rule would not always work. Sometimes it works, sometimes it doesn't. Okay, Ibrahim. So if the question is saying, hence, instead of thinking of the loop rule, you should actually use the result that you have in the previous part. In fact, when it says hence, you don't have a choice. You have to use the previous part because they've not said hence or otherwise. There's no otherwise option for you here. Hence means it's necessary to use this previous part. Okay. All right. 19, 6, and 4. And the older worksheet. Okay, question number 4 from this. You're done with the first part? Okay, so if we're done with the first part and are stuck at the second, let's think about this. So you're done with the first part, and in the first part, you have already... What's the problem? What's the problem with this, by the way? Because you already converted it to that form, right? So in the second part, you would just do that substitution now. Use this form now. You would say this is integration of cos 2 theta d theta. Limits for x are from 0 to 1. Now, that's something that you have to be careful about. These are limits of x, right? Because this is dx. The lower limit, so maybe you're not changing the limits. The lower limit is x equal to 0. And the upper limit is x equal to 1. The substitution is x equals tan theta. X equals tan theta. Now, if x is 0, just put this on your calculator. Tan inverse of 0, that will be 0. You get 0 here. 1 equals tan theta. Tan inverse of 1, put that on your calculator and you should get pi over 4 from that. Make sure to use radians always. Do not use degrees. You always use radians here. The limits are from 0 to pi over 4. So now you input those limits, 0 to pi over 4. Let's integrate this. Integration of cos is sine. That will become sine 2 theta divided by 2. That's the integration. Input limits from 0 to pi over 4. Okay. Now let's input pi over 4 limit first of all. Sine 2 pi over 4 divided by 2 minus sine of 0 divided by 2. 2 pi over 4, that cancels out to pi over 2. Sine pi over 2 is 1. So 1 over 2 minus 0, that's just 1 over 2. That's the result that we get. Okay. Did you forget to change the limits? Yeah. Okay. So you have to be careful. It's in terms of x. This is dx. Whatever variable you have here, limits are values of that variable. This is dx. Limits are values of x here. Okay. All right. That was 4-2. Let's move on. Six two. Is the same problem here? Did you remember to change the limits? In the second part? Because otherwise you would integrate this. When it becomes this, you have to integrate this using the cos identity that we did yesterday. You would say cos of 2a, that is identical to 1 minus 2 sine square a. So then 2 sine square a can be written as 1 minus cos 2a. So this would just become 1 minus cos of 2 theta. You integrate that with respect to theta, change the limits. These are limits of x. You can convert them to theta. You can do that, right? Right, so that's doable. Okay. All right, so let's skip this. So hopefully you can do this. Let's move on to the next one. Okay, question number 19 from the worksheet. Part 2. Part 2. So can you tell me the answer for the first part? values of A, B, C, and D? Answers to the first part. Okay, 1, 2, 1, and -3. Thank you. So now we have to integrate 1 plus 2 over x. Let's actually separate them to make it even easier. Integrate 1, integrate 2 over x with respect to x, and then you have 1 again. So you integrate 1 over x squared with respect to x, and then -3. So that's -3 over 2x minus 1 with respect to x. Okay, so these are the integrations that you have to do now. Integration of 1 is just x. So this becomes x. What about this? 2 over x. What does that integrate to? 2 over x. We can write that as 2 outside, and then inside we have 1 over x with respect to x. And that will become ln x, right? So this integrates to 2 ln x, the second term. Okay. What about this now? Integration of 1 over x squared. Any idea about this? 1 over x squared. Can we use any fraction rules on this? None of the fraction rules work on this form. This is actually the power function, because you can take this to the numerator and write it as integration of x power -2 with respect to x. With -1 power, we can't use the power rule, but with -2 power, we can use the power rule. And it will become -2 plus 1 divided by -1. So -2 plus 1 is -1 divided by -1. So use power rule in this to integrate. Okay, we could not use that here because it would have become -1 plus 1 divided by 0. That does not make sense. Power rule does not work with -1 power, right? So we use ln there. That's the third term. What about the last one now? This is log form. What's the derivative of the denominator? Derivative of denominator is 2x. Derivative of 2x minus 1 is 2. So we want 2 in the numerator. Can we have that somehow? I can write 3 outside. And then inside, I have to balance that, I would divide by 2 outside. So inside, I have 2 over 2x minus 1 like this. And now this is the ln form. Outside, I have -3 over 2. So the integration becomes -3 over 2 times ln of 2x minus 1. That's the integral that you have. You can simplify this first. It becomes x plus 2 ln x minus 1 over x minus 3 over 2 ln of 2x minus 1. And now you can input those limits. Limits are from 1 to 2. Okay, let's input the limits from 1 to 2. And then using log rules, we have to prove this somehow. So you see, you have only one log term here. Keep that in mind. That's something that you always have to do. Whenever you have multiple log terms in your final answer, you always write them as a single log term at the end. Let's input the limits so that it becomes 2 plus 2 ln 2 minus 1 over 2 minus 3 over 2 times ln of 2 times 2 minus 1. Subtract from this the case when you input x equal to 1, and that will give you 1 plus 2 ln 1 minus 1 over 1 minus 3 over 2 times ln of 2 into 1 minus 1. Let's simplify this. We get 2 plus 2 ln 2 Or let's simplify this first. 2 minus 1 over 2, that's 3 over 2, plus 2 ln 2 minus 3 over 2 ln of 3 minus 1, ln 1 is 0. So that's a 0, plus 1, and then plus 3 over 2 ln of 0, that's just ln of 1, which is also just 0. Okay, these two get cancelled. And we have 3 over 2 outside. We want 3 over 2 outside, right? We have that. Now here we have to get 1 over 2 times ln of 16 over 27. How can we get that? These two are different numbers. One way to think about this could be just take them to the power. Okay, so that it becomes ln of 4 ln of 4 ln 2 squared minus ln of 3 raised to a power 3 over 2. Is that okay? Until this point, we want an exact answer. Remember, we can't convert this to decimals. Now that we have no numbers outside, we can use the division law to write this as 3 over 2 plus ln of 2 squared divided by 3 raised to a power 3 over 2. Okay. What do we do now? We want this thing somehow. Let's think about it. In the numerator, we have 2 squared. We can write that as 4. In the denominator, we have 3 raised to power 3 over 2. That's not going to be an integer. What you can do is, since you want 1 over 2 outside, what that means is this 1 over 2 would have been in the power first, so that you can take that in the big, take that here, bring that here and multiply. So you want 1 over 2 power from this somehow. How can we have that? What's 3 cube? 3 cube is 27. So we can write this as, let me do it this way first so that it does not confuse anyone. 3 raised to power 3 over 2 can be written as 3 raised to power 3 times 1 over 2 like this. And then that becomes 4 over 27 power 1 over 2. All right. We wanted 27 in the denominator. We've got that. What about the numerator? If we want power 1 over 2 on top on 4, on the numerator, we can think of it this way. 4 is the square root of 16. So we can write 4 as 16 power 1 over 2. That's what 4 is. And now we can take that power common outside. So we have 3 over 2 plus ln of 16 over 27 whole power 1 over 2. And then this becomes 3 over 2 plus 1 over 2 using the power law. And we can write it like this, 1 over 2 times ln of 16 over 27. That's the final result that we wanted. The good thing about this is it's a 5-mark question. If you get to this point, you, or even the point before this, you already get 4 out of 5 marks. Okay. Then this is just 1 mark. You can skip some of these steps, but that would be the logic in order to go from this form to that form. Okay, but that will just be 1 mark. So don't spend too much time on this if you can't figure this out. This will get you at least 4 marks out of 5, and then you can do the rest of the questions in the exam first, and then come back to it at the end in case you have not figured it out the first time. Okay, any other questions? That was question number 19, part 2. Any other questions? No? No other problems? Rizal, how many questions have you done? Samiha, Saad, Safir, Amani. Where are the rest of them today? Do you guys have your mocks starting now? Is that why the attendance is becoming so low? Okay. Okay, what I'll do is I will choose a couple of questions from recent papers myself then, from the second worksheet. Let's do a couple of questions from that because I feel that most of you haven't practiced enough yet. So let's do some from some recent papers. Okay, so if you find any question like this in the worksheet, it happens sometimes. This first question, for instance, does not make sense because the first part of this question is not here, so you can't really do it. So you will just skip those questions, of course. Okay, let's do this one. This is question number 4 from this. When you have infinity as one of the limits. We studied this in paper 1, what to do when we have infinity as the limit, but we haven't done any question here yet. In paper 3, that involves infinity as the limit. So let's try this. This is from November 21. Okay. Question number 4 from that worksheet. Let's try this. It says using this substitution, u equals square root of x. Find the exact value of this integral. It's a 6-point question. Okay, Safi, but make sure to do practice if you haven't done yet. All right, we'll just do a couple of more questions and then we end for today. Just this question and one more. I'll see if I can find a more difficult one after this, and that's it. Okay, since you guys don't have any questions, it might not be as helpful as if you were to attempt the questions yourself first and then come with your problems. Okay, let's try this. The substitution that we are given is u equals square root of x. We can say that's x power 1 over 2. Let's find the derivative of this. du over dx, what's that? 1 over 2 x raised to the power minus 1 over 2. Okay. Now we also have to replace dx here. How do we do that? Make dx the subject. Let me write it like this first. It becomes 1 over 2 x power 1 over 2 and it goes to the denominator. And then dx can be written as, this goes there, so that's dx. This becomes 2x power 1 over 2 du. All right, that's what we have to input there now. Let's change the limits as well right now, so we don't forget that later. Lower limit and the upper limit. Okay, what's the lower limit in terms of x? X is 3, and the upper limit is infinity. U equals square root of x. So u would be equal to square root of 3 here. And if x is infinity, square root of infinity, what's that? That's also infinity. The upper limit remains infinity. Okay, now let's do that substitution here. It becomes integration of 1 over x plus 1. If u is x power 1 over 2, then what about u squared? U squared is x. So x can be replaced with u squared. So we have u squared plus 1 in the denominator times square root of x. That's also going to be u. Okay, now let's replace dx with this thing. That would become 2x raised to the power 1 over 2 du. And the limits are square root of 3 to infinity. Okay, just doing this much will at least get you 2 out of 3 marks, right? Converting everything, or maybe not this much, but x power 1 over 2, you replace that with u as well now, because we have to eliminate all x terms, right? This is x power 1 over 2. We replace that with u, and that gives us 1 over u squared plus 1 times u into 2u du. U and U get cancelled, and we just have 2 over this. I can write 2 outside, and that leaves me with 1 over U square plus 1 inside. With respect to U, we have to integrate this. Limits are from square root of 3 to infinity. Okay? Yes, Safi, you could do that as well. That should work. So you're saying you could replace this thing with 2 du directly. Yes, you could do that. So that works for this problem. So if you can figure something out like this in some question, you can do that. But this is the general way that will work for every problem like this, that you make dx the subject and then just put that in place of the dx that you have in that integral. Okay. But yes, in this case, what you're saying works and you can do that. You'll get the same thing at the end. 1 over u square plus 1 with respect to u. How do we integrate this now? This is tan inverse form, right? This will integrate to 2 times tan inverse of u. Right? This is the standard tan inverse form. And now you input the limits, square root of 3 to infinity. Okay. Now, what do we get from this? We have 2 outside. Inside, we have tan inverse of u. Now we input the limits, tan inverse of infinity. Okay. Minus tan inverse of square root of 3. How do we evaluate this now? Tan inverse of square root of 3, that we can do. Make sure your calculator is in radian mode. Tan inverse of square root of 3, I think that's pi over 3, right? Pi over 3. So this is pi over 3. What do we do with this now? Tan inverse of infinity. Tan inverse of infinity is 1. Why? Where does tan go towards infinity? Remember the tan graph? Looks like this. The tan graph, it goes like this, right? When does it go to infinity? At pi over 2. When cos is 0, yeah, you can think of it that way as well. Cos is 0 when x is pi over 2, right? So this is going to be pi over 2. You can think of the tan graph, or you can think of when cos is 0, yes. Or if you can't think of anything like that, another idea could be put this on your calculator. How do you do that? Tan inverse of infinity. We can't do that, right? Put a very large number and see what your calculator gives you. And that will give you maybe not because you want an exact value. But maybe it might give you a hint if you can't figure it out directly. It might give you a hint at least. So if you do something like this, for instance, tan inverse of a very large number. Okay. Let's see what it gives me. Okay, this is giving me pi over 2. Although it might be something close to pi over 2, but the calculator is actually giving me that. Okay, that's okay. Infinity, you can't input that in the calculator directly. In place of that, what you do is you put a very large number. So something like this, for instance, 10 raised to power 10. And you will get some idea of what it should be like from your calculator. It's giving me 1.57 here. That's half of pi basically. But if I increase this number, 10 power 20, now it gives me exact pi over 2. I can just use that value here. Pi over 2 minus pi over 3. And that should give us the result. Inside the brackets, this becomes pi over 6, right? 3 pi minus 2 pi divided by 6. Yeah, so we have pi over 6, and that simplifies to pi over 3. That's the exact value that we were looking for. Okay. Yeah, so it becomes an asymptote here at pi over 2. We cover this in paper 1. Right? Okay. One last question. Let's see which one looks the most scary in this worksheet now. You can suggest as well. I'll just scroll down and see which one looks very difficult. Okay, 12. Maybe we could have a look at that. I'll come back to that if I don't find anything else. This we just did before, question 18. Then here, x cosecant squared. Integration of that is this. This also looks interesting. X cosecant squared x and dy dx is this. Okay, let's do this. 25. This is slightly different questions. A slightly different question from the usual ones that you see. The second part of this. Question 25 from this worksheet. Okay, the last one that I'm doing today, and then tomorrow we start differential equations, and we will actually complete differential equations tomorrow, inshallah, because there isn't really much to that in terms of concepts, at least. So we will complete that, and if you have any questions on differential equations, we will be discussing them on Monday then, inshallah. And then it's iteration, and that's it. Then after that, we start M1 or S1, and then yearly past papers. 25 it was. Okay, question number 25. Let's try this. Okay, now the first part says by differentiating cos x over sin x, so that if y is equal to cot x, then dy by dx is equal to this. Okay, now what is cot x? Cot x is this, right? Cos x over sin x. So if you have to find the derivative of that, y equals cot x, how can we do that? We can write it as cos x over sin x, right? How do we differentiate it? We can use the quotient rule of differentiation. What was that? vu dash minus uv dash divided by v squared. This is u, this is v. Okay. Vu dash, v as it is, that means sin x as it is, into u dash, derivative of cos. What's that? That's minus sin. Minus uv dash, that means u as it is, cos x as it is, into derivative of v, derivative of sin is cos x, divided by v squared, that is sin square x. Okay, now let's simplify this. In the numerator, we have minus sin square x minus cos square x. What I can do is I can take minus common outside. That leaves me with sin square x plus cos square x inside. And in the denominator, I have sin square x. Sin square plus cos square, that becomes 1. So I have minus 1 over sin square x. Reciprocal of sin is cosecant. So we have minus cosecant square x. That's what we had to prove in the first part, that dy over dx is minus cosecant square x. All right. Okay, now they made us do that in the first part. And then now in the second part, they're saying, show that this integral equals this. Okay, how do we do this now? Part 2. Integration of x cosecant square x with respect to x. We need to show that this becomes 1 over 4 pi plus ln of 4. That's what we need to show. How do we integrate this? Any idea about this? X cosecant square x. It's a product. What options do we have for a product? Substitution, but we use that only when it's given in the question. It's not given in this question. What else? Integration by parts, right? Or that extended power rule, that also doesn't work because derivative of x is just 1. Derivative of cosecant square, we don't know. So that doesn't work. Integration by parts, that's what we can do. Okay. Now, how do we do integration by parts? Let's think about it. Why did they make us find the derivative in the first part? And then there's a 6 mark part after that in which they're asking us to integrate something that has that same function cosecant square x. Can we use that somehow here? The derivative of cot x is minus cosecant square x. If we reverse this, we can say the integration of cosecant square x with respect to x, that should be minus cot x. And if you notice, this is actually from 2019. They started giving this in on the differentiation page and from 2020 onward. On the differentiation page of the formula sheet, you see you have this written as well. Derivative of cot x is minus cosecant square x. We proved that there. If the derivative of cot x is minus cosecant square x, we can reverse this to say that the integration of cosecant square x should be minus cot x. We did that in our very first class as well on integration, that the integration of cosecant square should be minus cot x. Okay, but they've given us a hint there now that integration of cosecant square should be minus cot x. Okay, so that's what we can use. How do we use that? We can apply integration by parts in this. Let's use ILATE. ILATE. This is u, this is v dash. We have an algebraic function and we have a trigonometric function. That means u should be x and v dash should be cosecant square x. What's the derivative of x? U dash is 1. What's v? Integration of cosecant square x. This is where that is going to be helpful now, what we did in the previous part. Integration of cosecant square x, that is minus cot x. That's what we use here. So v is minus cot x. Let's use the integration by parts formula. uv minus integration of vu dash, right? Let's apply that formula. This gives us u, which is x, into v, which is minus cot x, minus integration of v, which is minus cot x, times u dash, which is 1. So we have minus x into cot of x plus integration of cot x. How do we integrate cot? Quickly? You need to remember this. How do we integrate cot? Using ln rule, right? Using the ln rule. So we have plus outside. Cot can be written as cos x over sine x. And now we can use the ln rule on this. We can say it's minus x into cot of x plus, we have the numerator as the derivative of the denominator. The integration becomes ln of sine x. And there we have it. We have integrated this now. Now we just have to input the limits. Limits are from pi over 4 to pi over 2. Cot function is not in our calculator, so we can replace it with cos over sine. Right? So that we can input limits easily. Cos x over sine x. And now input the limits from pi over 4 to pi over 2. We want an exact answer, right? Okay. Let's input pi over 2. Minus pi over 2 into cos of pi over 2. Divide this by sine of pi over 2. Plus ln of sine of pi over 2. Okay. Subtract from this the case when you have x equal to pi over 4. So that's minus pi over 4 into cos of pi over 4 divided by sine of pi over 4 plus ln of sine of pi over 4. Let's simplify this now. minus pi over 2. What's cos of pi over 2? Cos pi over 2 is 0. You can check that from your calculator. Cos of pi divided by 2, that is 0. So we have minus pi over 2 into 0 over 1, whatever that is, all of this becomes 0. Then we have ln of sine pi over 2. Sine pi over 2 is also 1. Sine pi over 2 is 1. So ln 1, this also becomes 0. Minus pi over 4 times cos pi over 4. Cos pi over 4 is square root of 2 over 2. Sine pi over 4, again from your calculator, is also square root of 2 over 2. So they get cancelled to give you 1. Plus ln of sine pi over 4. Sine pi over 4 is under root 2 over 2. Okay, now let's simplify this further. This becomes 0, this becomes 0. These two terms, they get eliminated. And we have plus pi over 4 times 1, right? This is 1, this cancels out, the numerator and the denominator. Plus ln of square root of 2 over 2. In fact, we have minus here outside. Minus ln of square root of 2 over 2. Now we think of what we want at the end. We want 1 over 4 into pi plus ln 4. That's what they wanted us to prove there, right? 1 over 4 into pi plus ln 4. Okay, now how do we go from this one to that one? This simplified would be pi over 4 plus 1 over 4 ln 4. We already have pi over 4 here. This we need to convert somehow to 1 over 4 times ln 4. Okay, now how can we do that? We want 1 over 4 there, and we want a plus sign there. Okay, first of all, let's make this plus, right? This is negative right now. We can make it plus first. How can we do that? We can take that negative to the power. So we have pi over 4 plus ln of square root of 2 over 2 power minus 1. What I'll do is I will keep this in front so we know what we want at the end. Okay, this is what we want at the end. The expression on the right side. And that's the final result that we want. Okay. So we have pi over 4 plus this. I took that negative sign to the power so that I have a plus sign here. Now, this will become pi over 4 plus ln of negative power means we can take reciprocal, right? This 2 comes here, this 2 goes there. And that gives us 2 over square root of 2, which is the square root of 2. Pi over 4 plus ln of square root of 2. Or we can say that is 2 raised to power 1 over 2. Okay. And then that is pi over 4 plus 1 over 2 ln 2. All right, let me just check if these two are equivalent or not. And then we'll see if... Okay, so let me walk you through my thinking process right now. So what I'm saying is I've gotten this point. And now I'm getting 1 over 2 ln 2, and they have 1 over 4 ln 4. So I'm just checking, are these two equivalent? Because in that case, I can then try to convert it to that form. If they're not equivalent, that means that I've done some careless error somewhere. I'll need to check for that first. So I'm just checking on my calculator right now if these two are the same thing or not. Okay, so that I can think of how to convert to that form then. Let's check that. 1 over 2 times ln of 2. That's 0.346 something. Okay. 0.346 something. And then 1 over 4. Okay, so these two are equivalent. 1 over 4 ln 4 and 1 over 2 ln 2. Both of them have the same value. Okay, so that means the working is correct until this point. Now we just have to think of how to go from this form to that form. Okay, so what I can do now is I can say, okay, pi over 4 plus, I want 4 here, right? I can say this is 1 over 2 into ln of 4 raised to power 1 over 2, right? 2 can be written as square root of 4. So that's 4 power 1 over 2. And now I can take this 1 over 2 outside as well. That gets multiplied with this 1 over 2. And we get pi over 4 plus 1 over 4 ln 4. And that's what you wanted to prove. That's our final result. And that's the integration. Is that okay? Any questions on this? Any problems, anyone? Okay, so that's it then. I'll see you again tomorrow. We will be starting differential equations tomorrow. Please make sure that you attempt all the questions, at least the assigned ones, from both the worksheets that are uploaded, so that if you have any problems, we can discuss them. But tomorrow we start differential equations. We will be completing all the concepts of that tomorrow, inshallah. And then if you have problems, we will discuss them on Monday. And the next week we get done with P3. And then we start M1 or S1 after that, inshallah. Okay, so the M1 and S1 classes, they will be starting on 7th of March, inshallah. Okay, 7th of March. All right, Allah Hafiz, everyone. I'll see you again tomorrow. Allah Hafiz.